So if the only information that we are given is f prime, we can integrate, but we still have that plus c. And really what we are finding is that the functions that have this instantaneous slope of 4x are a family of functions, in this case 2x squared plus c. So we don't know how it's being shifted up or down, but we do know for this one that the original function had to be a parabola, and it's going to be steeper. It's got that multiplying by 2, but it could look like any function in that family. So it could look like any of these. We just don't know which c value it's going through. We don't know how it was shifted up or down. So if I just have this information, my f prime, then I can't go any further. I'm saying, okay, it's this family of functions. It looks like one of these guys, but I don't know which one. However, if I have just one more piece of information, if I knew what point this goes through, so if not only I had this, but I knew it went through 0, 0, then I could find exactly what that c is. In that case, c would be 0. But if I knew one point that this parabola goes through, I could know exactly which parabola was the one in this situation. Okay, so we're going to do a few more examples where we can actually solve for c. So in this case, we've got the derivative dy dx equals this 2x minus 2. And then we also know that our original equation, which is what we're looking for, y goes through the point 3, 2. So that's going to be important when it comes to solving for c. So first we're starting with moving around our variables, multiplying that dx to the other side so that we can integrate both sides. And whenever we're choosing to integrate both sides, it's opposite operations. So it's like we're starting with the derivative, we're trying to go backwards. Just like when you have x squared on one side, it lets you know, okay, I need to take the square root of both sides. So we're integrating both sides. On this side, the integral of the derivative of y is just y. Or you could think of that as the integral of 1 with respect to y is y. And then over here, using our integral power rule, raising x to a power, raising it a power and dividing by it, raising our negative 2x to the 0 a power and dividing by it, so dividing by 1, and then we've got our plus c, our 2's cancel. Okay, but since we know that this function y goes through the point 3, 2, I can go a step further and say whenever I plug in 3 for x and 2 for y, it should make a true statement. And that means that I can solve for c. Okay, so we'll have this 2 equals 9 minus 6. So we get c is negative 1, and then I can go back to where I had y up here, and now we know it is the specific function x squared minus 2x minus 1. That is the function that not only has 2x minus 2 as its derivative, but it goes through the point 3, 2. Okay, one more example, and for this one we're going to be able to go a step further because we are looking for f of x. They give us ordered pairs on f and on f prime, but the function that we start with is f double prime. So in this case, just like when I start with f and I'm going to f double prime, I have to differentiate twice. To go from f double prime to f, I will have to integrate twice. So we will start with our f double prime equaling 3, but then I'm looking to integrate twice, and at each level I will need to solve for c. So I'll use my ordered pair f prime to solve for c there, and then when I integrate again, I'll use my f of 2 equaling 7 to solve for my final c. Okay. So with my f double prime, I am integrating both sides, and I do want to write that I'm integrating with respect to x, that the integral of f double prime will be f prime, and then raising my 3x to the 0 a power, we've got 3x plus c. And since we know that we are looking for more than one c, a lot of times they'll go ahead and make this first c a c sub 1, because we'll need to find a c for f prime and then also for f. So it's a good habit to be in to go ahead and make that a c sub 1. And now we can plug in what we know for f prime. So I know that plugging in 2 for our x's in f prime gets us 5. And we can use that to solve for c sub 1. Where c sub 1 equals -1. And then I can go back to, that tells me what exactly my f prime equals. So I have that 3x minus 1 for my c sub 1. And now I can integrate again so that I will have my original function. So integrating with respect to x. So my integral of f prime is f. And then using my integral power rule, my 3x squared divided by 2 minus x plus c. And since we already had our c sub 1, going ahead and calling this a c sub 2 is pretty normal. So now, using our final piece of information that f of 2 is 7, I can solve for the final c. So if I'm plugging in 2 for the x's, c sub 2, and let's see, we've got 12 over 2 is 6, minus 2 is 4. So we end up with c sub 2 equaling 3. And then that is going to bring us to our final answer, coming back to the function that I had right here. I'm running out of room because there's something underneath this. Where our final f of x is going to equal that 3x squared over 2 minus x, and then plus 3. Okay, so that is our function that not only has an f double prime of 3, but goes through the point f prime of 2 equals 5 and f of 2 equals 7. So right now we're just getting the hang of integrating. We can use it to go backwards and get an original function. So that could be useful for particle motion. If we have like the acceleration of something, we can find the velocity, or if we have the velocity, we can find a position function. So we can use it that way to just work backwards, but also integrals do their own things as well. So we've got lots of new stuff in the future that we'll be able to do with integrals. So get excited.